Okay, so I guess I'm gonna continue talking about some definitions of limits. Yeah. Okay, so a thing is in the first theorem that we're talking about is in R, all the real numbers. If first of all we have a set S that isn't the empty set, right? Then if it has a maxima, if it has a maxima, then it has something of a supremum. If it has a minima, then it has so if it has these things, then this has an infimum. Alright, so this is going to be a simple proof. Alright, so let's first try to prove it. So this is our line R, all the real numbers, and let's have our random set S. So it can be disentangled. So here's S, and obviously here's its maxima. Now I'm only going to prove it via maxima, since maxima and the minima are just, sort of the same. Alright, so let's try to prove that this works. So let's pick a random, maxima, since it has a maxima, and let's call this, I don't know, A1. And then let's pick a random, we're going to actually pick a not maxima. It can't be anywhere, so maybe I'm going to pick it over here. This is A1, and this one is B1. Alright, so we've just picked two random numbers. One is a maxima, and one is not. So, first, let's focus on this little part. This is our S. This is A1. Now, this A1 can be outside of this. You don't care. And this is B1. So first, we take A1 plus B1 over 2. If this is, exactly the supremum, then well done, we found it, okay? We found it. If it's not the supremum, which is most likely, and this is actually a maxima, this is a maxima, so maybe, it's pretty unrealistic in this graph, but if we just extend this, so over here is B1, and then the midpoint is this one. It's a maxima. Then we would define it as A2 is still equal to A1, and B2 is equal to A1 plus B1 over 2. So B2 is migrated over here. Alright, then we take, so this is actually also A2. Then we take another, part in the middle. So if A1 plus B1 over 2 is the minima, then A2 is going to be equal to A1 plus B1 over 2, and B2 is just going to be equal to B1. Yeah, this is going to be the new, since this one is a minima, A2, this is, in this case, A3 is going to be this point, and this is going to be B3. So a better case with this would be A1 plus AK plus BK over 2 is a maxima. Then A K plus 1 is equal to AK, and B of K plus 1 is equal to AK plus BK over 2. And if this is the minima, well, AK plus 1 is equal to, not bother to write this, AK plus BK over 2. Yeah, look at that. And, this is going to be equal to BK. Yeah. So this is our definition, and we're going to continue iterate this process over and over and over again. So eventually we have two sequences, AN and BN. These are the two sequences. Now, let's say our sequence AN converges. So the limit of AN is going to be equal to value A, And Bn also converges. Bn is going to be equal to a value B. Alright, and I mean, you have to also prove that these things converge, but I'm going to continue writing this. Okay, so then let's try to find another thing. Since the limit of n approaches infinity of am minus b of n is equal to 0, since they're going to get closer and closer to each other, so each time the distance is going to be divided by half. So this is going to be 1/2 of the previous before. So this is 2 to the, actually this is 2 to the n over 1 of the original a1 minus b1 absolute value, and the limit of n approaches to infinity. And you can try to find this out. This would equal to the limit of n approaches to infinity of value k. So this is just the constant k multiplied by 2 to the power of n over 1, which, 2 to the power of n minus over 1 approaches to 0. So we call this 0. Now so this value is indeed 0 over here. Yeah. Okay. So this value is 0. That means that a and b and eventually gets closer and closer to each other. So a is b. A is in fact equal to b. Yeah. Also, a proof of this eventually doesn't speed up to infinity, also works, since it's gonna be continuously halving or not changing for eternity. So it's gonna stabilize on some value, since eventual halving just equals 0. Yeah. Okay, so this is just a simple thing. A is now equal to b. So now we know that these things converge to the same point. All right. Let's change this value. So a is equal to b. Let's call this value m. So this is actually equal to a is also equal to b. So we're going to call this a new value. We're going to call it m. And for all x that's included in x, not x, s, so values that's going to be in this range. For all of these values, x would be smaller or equal to bn, right? Because bn is always a maxima. This is always a maxima. X is always smaller or equal to bn. That's a simple thing. So x eventually gets smaller than bn. And that's also the same thing. Since smaller than, it's always smaller than bn, so it also eventually gets smaller than bn. Only that eventually is right now, which is kind of confusing, but okay, stick with that. So that means x is smaller or equal than the limit of bn. That's going to be always smaller than bn. And we know what the limit of bn is. That's going to be b, which is m. So x is eventually smaller or equal to m. Okay. So x, any single x in the value, is eventually going to be smaller or equal to m. That's another thing. So next, another one. There exists a upper, so a maxima. There exists a maxima that is called m slash, which is smaller than m. So we're suggesting that m isn't this point. We want that m to be this point, but we're suggesting, does there exist a maxima that's smaller than m? Does there exist one? Let's see. So if it exists, then we say that the limit of an, since that is what m is equal to m, is bigger than m slash. Right. So that says an is eventually bigger than m slash. Right. Which basically also says an is bigger than m slash. It's eventually bigger than, an is always going to be smaller than m slash, it's eventually bigger than. It doesn't care. So even if it is eventually, it's going to be eventually bigger than. And since an is always increasing, but it still works all the time. So you can say that this sort of works. You have to make a big question mark over here. But you can work with the previous result. So AN is eventually bigger than M slash. However, AN is always going to be a minima. Well, we define M slash as the maxima. How can the minima eventually get bigger than the maxima? It's wrong. So there cannot exist. So there cannot exist M slash that will be smaller than M. There will not exist these values. So M is equal to the supremum of S. There we go. So the proof for the minimum, which is over here, is similar. It's almost exactly the same. Since the minimum is, it's so simple. You can even try to reverse the whole thing, change the bigger than to smaller than. It's pretty simple. Okay, so that's basically the proof of why there has to exist a M for the real numbers. Now this is for the reals, because some of these things might not exist in Q. For example, if our S is going to be the set 3 to pi, well, pi doesn't really exist. Pi doesn't exist in Q. And since pi doesn't exist in Q, well, we can't find a maxima, smallest maxima, so this doesn't work. In the real numbers, this does work. And yeah, that's STP of S. So we just proved that there must be a maxima in the real numbers. Okay, so that's just a simple proof.